After examining the four basic operations of add, subtract, multiply, and divide applied to functions, we're now going to move on to a new operation in section 3.2.2, composition of functions. Composition is an operation that I can apply to functions only. We do not find the composition of real numbers, so this is specific to functions. If f and g are functions, then the composite function or composition of f and g is defined by, here's how we denote it, f, and then we have a little circle that symbolizes composition of g of x. We read this, the composition of f and g of x, or f composed with g of x. Now, to evaluate this function, we're going to evaluate f of g of x. Now, before you panic, let me show you how the notation works. When we see a binary operator is a symbol with an element on either side. For example, when I see this operation, 3 plus 2, we know the value is 5. How do we know that? Well, it's so second nature by now you probably don't even think about it. But we have a binary operator. This symbol, which we read as plus, represents a certain way of combining the values on either side. If I change that symbol to 3 minus 2, we quickly can evaluate that to be 1. We get something different. How do we get something different? Because we've changed the binary operator. That symbol communicates to me a specific way of combining the values on either side of that operation. Okay? In the same way, we have a new binary operator. When I see that symbol, it represents a certain way of combining the elements on either side of that operator. And when I see that, it tells me to do this. What we have over here is called the composition of two functions, or we can think of this as a function of a function. Believe it or not, you have already found a composition in this class. Previously, we had defined a function f of x, and I told you to find something like f of negative x or f of x plus 1. You were plugging a function into a function. That's essentially what we do when we find a composition. So we're going to have an outside function and an inside function, and our functions have to stay in order. The function on the left becomes our outside function. The function on the right becomes our inside function. And we need to carefully preserve that order in the same way that we have to watch the order on certain operations. Up here, again, if I look at 3 plus 2 equals 5, if I switch the order, 2 plus 3, do I get the same thing? Absolutely. What if I switch the order with subtraction? Do I get the same thing I did with 3 minus 2? No, we do not get the same thing. Subtraction is not commutative, whereas addition is commutative. That means if you have a commutative operation, you can apply that operation in either order and get the same output. Like subtraction, composition is not commutative. That means if I reverse the order of f and g, I'm going to get something different, so I need to be careful about the order. Let's practice evaluating a composition. Example 3, let f of x equal 2x squared minus 3 and g of x equal negative x plus 3. If I asked you what type of function is f of x, what would you tell me? Did you say quadratic? If you did, you'd be right. I hope that you are talking out loud to me on this video. What type of function is g of x? Did you say linear? I hope so. If you did, you would be correct. Now, that's not necessary to work this particular problem. It's just good review. Okay, example 3, we're going to evaluate f composed with g of 2. What that means is we're going to evaluate f of, and I'm going to put g of 2 on the inside. F of g of 2. So we have two successive functions to evaluate, and we're going to start on the inside. On the inside, we're going to evaluate g of 2. Now, you know what that means, right? It's encoded instructions encoded in the language of math. It says, go to the function g and plug in 2 for x everywhere you see an x. So g of 2 is negative 2 plus 3. Let's go ahead and evaluate that. We would get f of 1. Now that we have evaluated g, f has been patiently waiting its turn. Now it's time to go to the function called f and plug in 1 for x. So using our other function rule and plugging 1 in for x, we have 2 times 1 squared minus 3, or 2 times 1 minus 3, which is negative 1. Okay, so when we evaluate a composition, we're really just doing two functions in a row. Notice we plugged in 2 for g, and we got out 1. We turned around, we took the output of g, and we immediately plugged it into f, and f spit out negative 1. So I'm just evaluating two functions in a row. So let's try that again, and notice on this second problem, the order is different. This time, g is going to be the outside function, and f is going to be the inside function. Now remember, the outside function waits patiently for its turn while I work on the inside function. Now, f of 2 tells me exactly what to do. It says go to the function called f and plug in a 2 for x. So we'd have 2 times 2 squared minus 3. Let's be careful to obey the order of operations. First, we would evaluate the exponent. 2 squared is 4. And then we would carry out our multiplication. 2 times 4 is 8. And then next we will subtract 3. So we end up with g of 5. Okay? So when we plug in 2 for the function f, 2 goes into f, 5 comes out, right? Now we're going to take the output of f and plug it into g. So next I'm going to use the function rule called g. So I'm using my second function, and I'm going to plug in 5 for x. We end up with negative 5 plus 3, or negative 2. So when we plug in 5, which was the output of f, into g, we get out negative 2. So evaluating a composition when you have a number in the argument position really is just like evaluating two functions in a row. But make sure you get your functions in the right order, because notice I didn't get the same thing when I changed the order. Now, the next example changes just a little bit. We're still working on composition, but notice now I'm looking at a variable argument. So this will be a more general case of evaluating a composition, but we're going to work it the same way. Pop quiz, f and g are both what type of function? F and g are both linear functions. Good. I'm going to assume you got that right. So to find f composed with g, I'm going to find f on the outside, g on the inside. Now, I'm going to start with the inside function. Please understand that is not g times x. That is the function g of x. I'm going to completely replace the function name, g of x, with the function rule, negative 5x plus 3. So the negative 5x plus 3 is going to go and replace that entire expression. Negative 5x plus 3. Okay? Now, f again has been waiting patiently. Now we're ready to evaluate f. The instructions here in code say go to the function f, so I know I'm going to be using this one. And I'm going to plug in the argument, negative 5x plus 3. Well, where am I going to plug in that argument? I'm going to plug in the argument where I see the variable. So I'm going to put a box around that variable, and I'm going to show you that everything in parentheses is going to land in that box. When I evaluate a function, I drop the function name. So we're going to get 2 times. Now, here comes my box. I'm putting negative 5x plus 3 in the box, minus 3. Okay? So let me do it in red. My argument that I had here is getting plugged into this red box, and I'm applying the operations to that new argument. So just for a minute, look at the function f of x. Okay, f of x says 2 times something minus 3, right? And what do I have in my evaluation? 2 times something minus 3. So I've got the same details, but a different argument. So once we have everything plugged in, then our job is to simplify. So let's distribute our 2 to get negative 10x plus 6 minus 3, and combine like terms to get negative 10x plus 3. So the composition of 2 linear functions produced another linear function. That's worth practicing again. Notice on example B, we're switching the order of our functions. G is on the outside, F is on the inside. If you will write the same steps in the same way that I do every time, you will learn the rhythm and this won't be too difficult of a skill. So I'm going to start by replacing f of x on the inside with what? What's going to replace f of x? F of x gets replaced by its argument 2x minus 3, right? Then I'm going to go to the other function called g, and I'm going to plug this into the argument. So I'm going to use g, and I'm plugging the argument in for that variable. So I'm going to put the red 2x minus 3 in this red box. So we end up with negative 5 times, here comes the stuff into the red box, 2x minus 3. And then everything else in the function stays the same. Okay, so we have in g of x, negative 5 times something plus 3. We have the same pattern here, negative 5 times my new something plus 3. So the overall details are the same. The operations, I'm just changing the argument. Okay, we are home free. All we have to do now is simplify. This becomes negative 10x plus 15 plus 3. And combining like terms, negative 10x plus 18. So again, we've composed 2 linear functions and have obtained a linear function. Before we move on, let's do one more example. Now we have functions d of x and a of x. Functions can be named anything, and oftentimes in practice, they're named for what they model. So d of x might be diameter. For example, a of x might be area, something like that. The argument or variable is x. Find the following, d of a of x. So d is my outside function, a is my inside function. So I'm going to start, remember, the outside function waits until step 2. I'm going to start by replacing the inside function a of x with its rule x minus 5. Then I'm going to go to the function called d, and I'm going to plug in what I have in parentheses, the argument x minus 5, in where I see the variable. So x minus 5 lands in that blue box, and all the other details stay the same. So we get x minus 5 plus 3. Let's simplify. Negative 5 plus 3 is negative 2, so we end up with a radical function. Now let's go the other way and evaluate a of d of x. So a is on the outside. We postpone that until step 2. And then we're going to replace d of x by its rule. D of x gets replaced completely by the square root of x plus 3. Okay, interpreting the code here, now it says go to the function called a and plug in the new argument where you see the variable. So I'm going to take that square root of x plus 3 and put it in that blue box. I get the square root of x plus 3 minus 5. Now, some of those numbers are under the radical. 5's outside of the radical, so there is nothing there that I could combine. So I am done with that problem. Now, before we move on, let's just review really quickly. What if I asked you the domain of this function? Do you remember what to do? The domain of a radical function is obtained by setting the radicand greater than or equal to 0. Remember this? This wasn't part of the problem. We're just reviewing. So if I put this in interval notation, we would end up with 2 to infinity. So this is saying I can plug in any number bigger than 2. If I plug in a number bigger than 2 right there and subtract 2, the radicand would be positive and the output would be real. Okay, how about example B? What's the domain? Well, I'm going to take the radicand out and set it greater than or equal to 0 and very easily solve for x. So x greater than or equal to -3 in interval notation would be -3 to infinity. Okay, let's move on to example 6. We've got f of x equal to 2x squared minus 3, which you would tell me is a quadratic function, and g of x equal to -x plus 3, which is a linear function. We're going to find f composed with g of x. So f is on the outside, g is on the inside. So I'm going to start by replacing g of x with its rule, -x plus 3. Then I'm going to take that argument, -x plus 3, I'm going to plug it into the function called f where I see the variable. So -x plus 3 lands in the blue box. Looks something like this. Our job now is just to simplify. Now be really careful here. Make sure you evaluate the exponent before you multiply by 2. You cannot distribute that 2 until you have evaluated the exponent. And we're going to evaluate that exponent with FOIL. So foiling, we have x squared. Outside is minus 3x. Inside is minus 3x. Last is plus 9. Combining like terms in parentheses, we have x squared minus 6x plus 9. Now we're ready to distribute the 2. We have 2x squared minus 12x plus 18 minus 3. And then combining constants, we get 2x squared minus 12x plus 15. Woo, that was a lot of algebra on that one. Let's see if this one turns out the same way. G this time is on the outside. F of x is on the inside. So remember, g hangs out and waits patiently for its turn. And we replace f of x with its rule, which is 2x squared minus 3. Then I'm going to go to the function g. I'm going to find the argument or the variable, and I'm going to plug what I have in parentheses into that blue box. So we have negative parentheses 2x squared minus 3 plus 3. In this case, we need to distribute the negative to obtain negative 2x squared plus 3. And combining our constants, we have negative 2x squared plus 6. And that one was much easier. But do notice, when we change the order of composition, we do not get the same thing. So order is very important. Okay, good job.